Hi, everybody. Thanks for joining us. I'm Dave Ferguson, Dean of the Estopinal College of Architecture and Planning, and we're pleased to welcome you to the second hosting of the Ethan Whitehead Guest Lecture in Sustainability. So this event will conclude our college lecture series, so ending with a bang. And this year, I don't know how many of you got a chance to see a lot of the speakers, but we really had a stunning cast this year. So for students, stay tuned. Next year, I think we're going to have a great lineup as well, and I'm really looking forward to hearing today's speaker. So as many of you know, this event commemorates our student and friend, Ethan Whitehead, who passed away in 2021. Ethan was a second-year architecture student and had a driving interest in sustainability. His family generously established this event as a way for Ethan to share his love of sustainability with his fellow students, faculty, and others. So I'd like to recognize Ethan's parents, Julie and Doug Whitehead, who are here with us today. Thank you for joining us. I also extend our thanks to President and Mrs. Mearns, who are here, and Provost Mari. Thank you for coming today. So the UN issued a report last fall that stated, quote, "The building and construction sector is by far the largest emitter of greenhouse gases, accounting for a staggering 37% of global emissions. The production and use of materials such as concrete, steel, and aluminum have a significant carbon footprint," end quote. So, innovations, such as you're about to hear about from our today's guest, Nat Slayton, have never been more important, and is going to become a basis for how we design in the future. So here to introduce Nat is our own expert in mass timber design, Professor of Architecture Pam Harwood.
Definitely not an expert. But thank you very, very much. And it really is an honor to be here today and to share this moment with all of you. I'm really excited to introduce Nat Slayton as the second Ethan Whitehead Guest Lecture in Sustainability in the Estopinal College of Architecture and Planning. Growing up in a small Oregon town, Nat is from a family of loggers, carpenters, and architects. Not hard to imagine his love of the natural wonders of Oregon's forests and rivers and coastline, as we shall see illustrated in his lecture entitled Crafting Community, Portland Airport's New Terminal Building and the Potentials of Contemporary Architectural Practice. But Nat's career path into architecture was not a straight line, as he ventured into other professions first, like his brief foray into Russian literature. Nat did undergraduate studies at the University of Oregon in Eugene. Interestingly enough, his studies were in a building adjacent to Lawrence Hall Architecture Building, which he found ultimately more interesting. What brought Nat to the discipline of architecture, he says, was the intellectual curiosity architecture requires and the ability to shift between aspirational visions and functional specifics. We can all relate to that, can't we? Nat went on to receive a Master of Architecture with distinction from Harvard University Graduate School of Design. Before joining ZGF, Nat worked in the offices of Rem Koolhaas, OMA, in Rotterdam and in New York. Nat is particularly inspired by large, technically complex projects. He believes that with scale comes opportunities to engage broad fields of expertise and to guide collaborations that result in spaces that are beautiful, timeless, and responsive to a changing world. For the past 20 years at ZGF, Nat has helped lead the design of some of ZGF's most challenging projects. He's got a strong technical and design background and guides collaborations amongst designers, engineers, builders, and stakeholders, working across disciplines to discover opportunities and unexpected solutions. The challenge of Portland Airport's specific local character and its focus on sustainable initiatives And the challenge for Nat and the team at ZGF was, how can I strengthen the airport's connections to a local economy, reduce its carbon footprint, doubling in capacity, all while keeping the building open, really, and passengers moving smoothly through it. I'm really excited to see the 8-year process that Nat has had working on the airport. It's long spanned 9 acres of wood, this roof that's prefabricated off-site and creates an incredibly moving experience for all those who transfer themselves underneath it. But it also is creating a high-performance window system that maximizes energy performance and allows the building's structural resiliency as it moves, moving up to 44 inches. Can you imagine a building moving that far? And finally, it has to links to Portland and to Portland streets and its regions and its rich tradition of craft and fabrication. This does seem like a daunting task, but one that Nat Slayton is well prepared to share with us today. So please join me in welcoming Nat Slayton to the podium. Is it okay?
Okay. How's this? Can you hear me? Great introduction. Thank you, Pam. I've probably got too much to talk about because, as Pam said, I've been working on one project for 8 years, which is kind of bonkers in architecture. One of my closest friends in Portland is a Ball State grad, Doug Sheets. He and Molly both went to school here, I don't know, almost 20 years ago, probably 24, 25 years ago, right? Doug has got about 6, 7 projects at any one time. And that kind of tells you what architecture can do to you. You know, you can work on a mega project, which this is. It's a very big project with a huge budget, thousands of people engaged in it any one day. But you can also be responsible for a smaller project, you know, and when you're responsible for a smaller project, you're often involved in many kinds of decisions simultaneously, and you're responsible to many kinds of stakeholders simultaneously. So both are extremely challenging. I really want to thank the institution for inviting me. This connection came through initially, I think, Carl Sonnenberg, who's a partner at my firm, ZGF, in Portland, Oregon. And oddly, Portland has a lot of connections to Muncie. First with Carl for me. Carl Sonnenberg is a grad of Ball State. Also Victoria Nichols, who's another partner at ZGF. She's in Seattle and leads our healthcare practice, which is a huge, huge practice within our firm, which I'll share a little bit of. And people like Doug and Molly, who moved to Portland. There's this kind of flow of people that has happened from this place, which I think is special. And I want to thank you for inviting me to kind of witness that, because witnessing is what I've done today. I've seen these people in Portland. I'm like, what generates? What is it? What kind of stew is creating such kind, nice, thoughtful, but kind of very, very, I would say, practically oriented, but thoughtful, especially people. And it's this place. So it's really been wonderful to see that. And as the speaker said last year, Dr. Fleming, this lecture series has that opportunity to kind of project out, right? Inviting people in and then projecting the legacy of Ethan and that interest in sustainability back out. And I will take this with me and share it with my colleagues in Portland and then my colleagues across my firm, which is almost 800 people now, you know, across the United States. You know, I think that is really special. And I also want to acknowledge, I spent most of my day, thank you, Pam, in a studio, which I haven't done in 25 years, you know, in studio space up on the 4th floor there, working from one end for the second-year students to the other end, which seemed like every third person was named Nathan, which I think is fantastic. That's great. But the thing I saw, which kind of blew me away, was actually the desks, right? How the students have a laptop. They have a physical model, almost everyone. A physical model, messy, you know, cuts, you know, tapes, glue, all that stuff. A CNC machine, which I didn't know, that you can buy on Amazon for like $200 and it just gets delivered in one student. I forget which one had like the kind of Cadillac version, and he was kind of embarrassed to show it, but they have like their own factories on their desks, and they're all like this. And then they had the opportunity to go to the construction management school. Hopefully some of you showed up. Anybody from the construction management school here? Raise your hand. Hopefully we get some of them here, because that was also great. Had lunch with them. We had sandwiches and salads, and I talked about what I think is, and my contracting colleagues doing construction think is one of the most remarkable construction projects in North America right now, which is this project. And the thing that I mentioned to those students was that, for me, growing up in Oregon, we have two state schools, University of Oregon, well, two of the main ones, where the design school is, architecture school, and then Oregon State University in Corvallis, 45 miles away, which is where the construction management program is. They don't talk to each other, right? These students never get to collaborate on anything, right? There's not a connection there. And on this campus, the connection is a short walk away. And in fact, you're all part of the same program now. My job, every day, I'm in the same room with those people. So having that connection is fantastic. Like, that is awesome. So you've got it all. You've got the desk with a little mini factory. You've got your contracting friends right down the quad. And I'm very envious of that, and I think it bodes well for all of you. It's really awesome. And what I'm going to talk about today is why that's important, right? Because doing architecture is first and foremost about relationships. It's about working with people and teams, right? Nothing gets done without teams. And knowing how to operate in a team context and being a team player and kind of all understanding what goals and objectives are and how to negotiate to deliver something amazing, that's what architecture is. So that's our responsibility, is to kind of get to something new, right? Because we work in teams and we work collaboratively. That's very much what this story is here. So I'm going to try to get, so Portland, Oregon, it's on the coast, it's in Oregon. It was recommended that I show this slide to help people that might need that orientation, but it's 2 flights. I learned that yesterday. Go to Chicago, then you pop down, you go to Denver, and you pop over. But critically, it's in the Northwest, right? So all of your kind of associations with the Northwest matter. Oregon is very much about trees, right? It's very much about trees. Its economy is rooted in this place, right? In the forests that surround these cities. But it's also very much about that, exactly that, the cities and the forests, right? So that kind of rural-urban kind of relationship is extremely important. And those two economies and how they relate to each other and the kind of politics there is very important. And has a long history of also being rooted along its river. Columbia River drains, half the United States, it seems like. It's the second largest river in the United States, and has always had a relationship to that river. This is Celilo Falls, kind of near Mount Hood, where, for thousands of years, the native populations would fish there, and in the 50s they dammed it and they lost this, right? It's also rooted in industry, right? There's a long history of making things in Oregon, and especially along that river. These are the Kaiser shipyards and along the Columbia River in World War II making the Liberty ships, right? They pump these things out like 1 every 2 weeks or something. But to do this requires first people that know how to work with steel and people that know how to work with wood. Because you see the false work for this is all wood, right? So both those things are here, and you'll see both those things are in the airport. Oregon is known for, obviously, the kind of iconic stuff is the big wood, right? So that this doesn't exist anymore. These are old growth logs, right? They're on the right there, and old growth forests on the left, most of which is gone, like 95% of that's gone. But we're still left with managed forests. But this image and this iconography is still very important to people in Oregon, but especially to kind of emphasize that it's also this. Intel is the largest employer in Portland, right? They have huge multi-billion dollar fab shops there in Portland, just outside of Portland. So it's high tech plus, rural economies, plus kind of extraction economies, both things simultaneously, so we're together, like we rely on each other. And our DNA is very much this. On the right, this is one of the kind of log barges, which were kind of where all that forest lumber was pulled out of the forest and sent down along the coast of California to build LA, to build San Francisco, 1890s. And then the thing on the left is the money that was made from that, built a city, built a pretty nice city downtown. This is what we call our Benson bubblers, that the kind of a public amenity on the sidewalk, just a water fountain, but a beautiful water fountain that goes every day of the year. The same person that made the millions of dollars sending those logs is Benson, the person that did that, right? So that there's kind of an investment in the community on a very kind of intimate level by the captains of industry, which were in the extraction side of things. Now, this project that I'm talking about today is airports. Airports are, first, nodes. There isn't a line from Portland on the left there to Indianapolis there, but you get the point here. The airports are nodes. First, they are just nodes and networks, right? And as nodes on networks, they could be extremely anonymous, right? They could be just a connection, and that's all they need to do sometimes. This is the important stuff of airports, right? It's the technologies that help passengers and people kind of find their way to their plane, right? To get processed. It's processing of people to get places. So they could be extremely generic. This could be an airport. This could be the lobby for the DMV, right? But it could be that. And sometimes it is, right? Airports sometimes are just drywall and terrazzo, but they're also sometimes this. They're sometimes front doors. And this is like, here you see some of the most iconic front doors in the world. You see Madrid on the top left. You see Singapore on the top right. You see Geneva, which I visited last year, which is astonishing, like space on the bottom left, and Hong Kong, which kind of set a new standard for what an airport could be in the bottom right. All very different, all a little bit more specific to the places they are, right? And that's something we were very interested in, is like there's some rules when you're doing an airport, the things you need to do, but there's also a lot of freedom. And so it's the freedom to kind of express the place that we drove at with this project. Like how do you get at defining a front door? And how can you, in the defining of that front door, how can you bring industries into a mega project? Because like building a cathedral, say, a mega project brings opportunities to do something radical, right? To kind of like you're lifting up, in cathedral's case, 15% of the economy of an entire region, say, which brings with it workers, right? Expertise to kind of accomplish that mega project. We also had the opportunity to kind of do something radical when we did the airport, to kind of think differently about how you do the job of architecture, how you do construction differently. First, I want to talk quickly about ZGF. So ZGF, based out of Portland, started in Portland. It's kind of the origin story of ZGF. We started in Portland. We started working in the region, doing primarily institutional work, hospitals, city halls, the kind of the public side of the city. Eventually got into transportation, light rail, to develop the light rail lines in Portland, and then expanded along the West Coast, first to LA, then Seattle, and then more recently Vancouver, and then opened up shop in DC, and in DC been very involved in kind of embassy work in larger projects. Amazon, for example, Amazon's headquarters too was done by ZGF, and then especially research projects. All of these things have two primary focuses, though. I would say three, actually. So ZGF, because we're multidisciplinary, we're architecture, we're interiors, urban planning, sustainable design, graphics and data analysis and fabrication shop. We got a huge fabrication shop. It's kind of like all of these kind of crazy people together. Because of that, everything we kind of have a manic interest in doing things that are extremely specific, right? So very specific to the place, the people of any community. There are no, and this is like there are no signatures at ZGF. There is no primary designer. There's many designers, right? And the whole point is that you kind of work with the stakeholders, the clients, the communities to be as specific and responsive as we possibly can with each project. These are all recent projects, well, most of them are recent projects by ZGF. Picked them out almost randomly. Top middle is Microsoft's headquarters, which was done in the late 90s. Then a small community center for a student camp, a kind of a youth camp in Oregon. A research building for Cal Poly, Nike's world headquarters, and a hospital in Seattle, a children's hospital in Seattle, right? Which Victoria Nichols, Ball State, was the lead on that one. But that's the point, as specific as we can possibly think to be, with any given project, and without approaching it with ego, with just kind of coming in and saying, how can we get to the right thing here? To do an airport, also just acknowledge, obviously it's not just me, right? We were the largest, the project, just the architecture side was the largest project, like a big, second largest office in the state of Oregon while it was kind of full bore. We had 67 people in Portland working on just the one project. So, and that's just architects, right? So we had hundreds more who were our engineering partners, and then the contracting side also hundreds more, so it'd be huge teams. And so how you organize that team and how you kind of thought about making decisions and getting to consensus was a big part of this thing. Now stepping back in the challenge, what are we up to here? So Portland had kind of thrown at us this like almost impossible challenge, like, hey, we're already the best airport in the United States, according to Travel and Leisure. We already have an identity. It's the carpet that people walk on and put on Instagram when they arrive in Portland. But we want you to kind of, we got to rebuild, our main terminal. Help us out here. And so the question is like, well, how do you improve on that? Like you're already number one in most metrics. Like you already have your gig, your identity already defined, at least in the kind of in the cultural sphere. And just get some background. So this is what the project is. It's like, it's an airport, right? And we've got to replace the thing in the red there, the terminal, like the heart. We're working on the heart. We're doing open heart surgery. An airport can't shut down, right? So you got to stay open. And more kind of context. An airport involves concourses, it involves a terminal, it involves a central utility plant, but also it's got space around it. And we'll get to that thing on the left there later, but space around it became important in this project. So the ask of us was hey, like many large pieces of infrastructure in this country, we got a problem. Like, we're running out of space, we got nowhere to grow. We've heard about this big earthquake that's coming. We're just burning all kinds of fossil fuel. So, but we've got to basically double our passenger capacity, get to 35 million by 2045. We've got to do all that, grow in place. We've got to set up a new structural system which allows us more flexibility, because with technologies coming in, especially biometrics, it changes how people move through airports, right? And so queuing is changing, the space needs are changing. We got to do all that, but still save what's good about Portland, save our heart, what is giving us our identity. And by the way, we want you to double the kind of operational footprint of this thing in capacity, but can you also cut the energy use in half? Figure out a way to do that. And also, come in on budget, but kind of include as much of the local industry as you can in this thing. We want you to like maximize, let's hundreds of contracts to local people, like not just a few, but let's just really push this. And then no planes can be turned away while you do it. Like everybody's got to make their flight, right? So, okay. So here's the graph of that. So the projections for growth, and this is probably typical of many airports. We were kind of operating this quaint little world of 10 to 15 million passengers annually for our town, and which was similar, I guess, to Indianapolis's population. We had a kind of all these projections, planning projections we had done of like, well, what if? How much capacity do we need to accommodate in this new terminal? Because the terminal is, because you're processing, it's the valve, right? It's the thing that kind of sets up the rate that you're moving people through it. And then we had COVID hit, and it was like, oh, well, all of the math you had done doesn't make any sense anymore, so what is the right thing? Well, the right thing is be as creative about flexibility as you can. which is what we did. And there's also this problem, change. So what does it mean to make something new? Well, it can mean, especially as more and more stakeholders get involved in decision making, it can mean you wind up with the same thing and it's just bloated, right? And so how do you manage that? That's managing decisions, right? To drive at something that's efficient, because the thing on the left does the same thing as the thing on the right does. And then there was this geologic context, which we'll get in a little here. So Pacific plate on the left, Juan de Fuca plate on the right. So the green is Oregon, California, Washington. The left is the Pacific Ocean. Pacific Ocean plate is sliding underneath the Juan de Fuca plate. And that means that, like most of the Pacific Rim, we've got volcanoes and earthquakes in Oregon. We just haven't been hit real hard recently. But there was this article that made the front, it was a huge article in the New Yorker about 5 years ago now, by a geologist at Oregon State University who said, hey, I'm measuring, doing tree cores in the Seattle Sound there, and he was finding that actually there was this period, this kind of regular period of earthquakes going back 10,000 years when he was looking at kind of major events that seem to have evidenced themselves in trees that got submerged. And he's, it's actually very regular. Basically, it's like every 500 years you get over a 9, and every 250 years you get somewhere like between an 8 and a 9. Now, an 8 would devastate Portland. A 9 would level it. Like, it would pretty much take out every building in the city and every bridge in the city. Like, it would just flatten them. And it would create a tsunami. It would work its way almost up to this, from the Pacific Ocean up the river to our downtown. And what was a little kind of alarming, that the article created quite a bit of alarm in the structural community on the West Coast, because you saw the gap. Basically we had a big one about 250 years ago, and there was some Native American village that they found that slid down the hills in Washington. There's evidence of a big one having happened, but we haven't had one since, which means we're due, right? We're due. This will happen. Like, there will be a major earthquake in Oregon in the next 50 years. It's just how big. And this is what it means. When there's a major earthquake, and especially when you're building along the Columbia River, it means you will get liquefaction. Liquefaction means your foundations will tend to settle. And so when they settle, you get catastrophic collapse, right? So the way you design to this is the things on the left, the piles, those are the vertical there underneath the foundations, they get very deep. And so our project kind of addressed this by setting up a foundation which could withstand liquefaction and drive those piles so deep that you got below the soils, which would kind of move. The other last context I want to bring up is documentation. So the thing on the left is a contract document, right? Set of drawings. This is a 3,000 sheet set, which was the largest that was ever been done in Oregon. And the thing on the right is a model, which I saw on the screens up there as I walked around. The interesting context here is that, like, we operate now in the world of the model, and the model means collaboration. There's 250 models that are federated. They come together. Well, that means you're working with the people building buildings simultaneously as you're designing, so that everybody's included, because you have to be, and you're designing things in the virtual sense, right, together to come together. So that has radically changed how we collaborate as teams. And then cost, right? So we also kind of did this diagram at the start of the project to kind of illustrate that the roof that we see many pictures of is only 3% of a budget. And a tremendous amount of the budget are things you never touch or see, right? It's logistics, it's enabling, it's insurance, it's like additional scopes that kind of get crept onto the project to allow things to happen, right? And so managing the thing on the left, or at least designing around them, gave us a kind of a new voice at the table, like, hey, can we focus on this thing on the left, not just that little slice thing up there on the right? Yes, it's expensive, but if we could figure out a better way to build it, maybe we could drive that cost down, So here, just want to get at the plan a little bit. So airport, you get dropped off. This is the existing building before we got into it. Ticket hall, kind of common retail space, and then you split north-south security, and then you're off to your airplanes. That was built on top of many buildings that grew over time, like many pieces of infrastructure. 12 buildings ultimately, stitched together, each with their own structural problems, each with their own collapse problems, each with their own architectures and identities. And our mission was to kind of like, well, create something new out of that. Those structures are represented here. And the blue is actually baggage handling system. So when you go to the airport, the baggage handling system is below you, right? You often don't see it, but it's the thing doing a lot of the work. It's kind of the nerves of the building. When you build over this thing, you can't really touch much of that. You got to kind of come in with a light, just surgically work your way through all this stuff. And so what we kind of think, like, stepping back with our new plan, well, how do you, if you're operating on a new scale and you've got to order things in a new way, and you've kind of taken 12 buildings and creating one space, what do you start with? And what we started with is an idea about thresholds, because you go to airport, you get your ticket, you go to security, concessions, and then to the concourse, right? Thresholds of space, thresholds of stress, thresholds of kind of different kinds of processing, and using landscape and materials as a way to kind of make something of those thresholds, so that there was more of an intuitive way to move through the space, not just relying on signage, but using the landscape as to create an intuitive organization. So this drawing has no structure, it has no roof, it has no floor, but it's just how do we create moments in this plan which help to define the important big spaces in the project. And we wound up with this, which was, again, you come in, there's ticketing, but it's flipped around. And then you get this moment of wood floor and landscape, and then this moment of there's a market where place where people can get together here, and then you go security north, security south, and then you pop out and get your shoes back on under trees. You got some concession spaces, then you're off to your Alaska Airlines flight or your Delta flight or your United flight on this side. But it's set up using materials and landscape especially, and crafted elements to create big spaces. So it's like you're setting up a very big volume with small little interventions of buildings, landscape, materials to help people understand where to go. Because oftentimes airports can be confusing, right? So we wanted to make it real straightforward. Ideally you don't need signage, right? And these are those big rooms. So it's like a big volume. This is a 9-acre space. 1,000 feet by 400 feet or so, but organizing principally kind of these spaces, a ticket hall, a market and security area where the queue can kind of flex, it can grow into this space or stretch out of it, depending on the holiday season, say. Then you leave into the concessions area, and if you arrive into Portland, you come down these concourses and you'll pop out here into this kind of landscape element, and then down to get your bags and leave. So the idea is it's hopefully super straightforward, right? And it just makes sense when you're there, when it doesn't need a lot of articulation at the scale of, say, graphics or signage. And then this is the kind of setup here, which starts to introduce the idea of this roof and the sizing of it. Now, as I mentioned, we could only come down a few spots. And what does it mean to do that? Well, it means you've got to come up with the right spans for structure to thread through that existing building. And in our case, we traveled around the world and we looked at what does it take to set up a ticket hall. Well, it takes about 100 feet here. And that's, imagine your ticket agents, right? You're checking in your bag, you're waiting, you have a queuing area, and then you have circulation areas between this, which gets you moving through the ticket hall. The other scale is 150 foot, which allows us to stack security lanes with no columns, so that the TSA, because they're always changing how they set up these things, has flexibility to grow and as they change technologies. So this space is meant to be totally flexible, so they can, and this is where it's headed here, is biometric. They can kind of introduce biometric technologies to help you pass through quicker. And that sets up an idea of a grid, like to overlay over this new building. So, but first I want to talk quickly about the structure, the kind of like, that was the structural interventions, and then there's the systems. Like, well, how do you also get at the carbon question here, and growing, but also reducing the energy footprint of this building? And here's the kind of the summary slide of that, which is that we focused on the primary systems of the building, which is the central utility plant. We focused on creating a high performance envelope to take down the cooling loads of the project. We focused on the roof. It's a big roof, to kind of like, oh, how do we maximize daylight underneath this big thing? And how do we basically allow that you kind of operate this little airport without turning lights on if you really needed to? So we kind of came up with the idea of a series of different kinds of skylights. And then materials, bringing in those local materials, bringing in the low VOC materials, bringing in a lot of things that people would actually want to be around as they're occupying the space. This is that geothermal. So the cool thing with this, and this is like hopefully the least graphically compelling slides I've got, but it's probably the most important. Existing facility, major facility, piece of infrastructure has a central utility plant. The central utility plant has this kind of legacy steam system, right? Super carbon intensive, not good. But it has all this piping that's fantastic between it and the airport. What we did is basically kept this building from the late 50s, like this old central utility plant, stripped out the boilers and replaced them with heat exchange units, and an airport's got a lot of land, there's places to drill geothermal wells, so we had injection wells as an open loop system, injection wells and extraction wells, which we connected to that central utility plant, and then used that steam piping that had been steam, converted it to low temperature water, right? And just used the same system that was already there. Just by converting to heat exchangers in their existing central utility plant. Well, you'll ask, well, what happens when you build this thing? Well, we're doing it in a very schedule-specific way, right? We're headed towards the summer right now, so cooling is still important. But we're kind of setting it up so that switchover in terms of the systems is very quick, and we can do it. But it's kind of this really smart little game that our mechanical engineer came up with to use what they have, right, and backfeed the existing distribution systems, which takes us to this, which is our EUI, which I was asked about by one of the students, which I really appreciated. I appreciated seeing all that data this morning on their screens, and I was embarrassed to share that, we start at 200, and that's a number that's not even in their radar. They're kind of operating down in the single digits on the projects here. But airport, that's pretty typical. And then this is an energy use index, which is like a BTU per square foot. It's a metric to like how energy intensive is your building kind of thing, right? And we were able to, with geothermal, kind of drive under 100 and then kind of work our way from 100 down to 89-ish as we electrify more things, as we, with a high performance envelope, with kind of very efficient lighting strategy, kind of just pick at it until it gets to 89, which is really good for an airport. And then there's the embodied carbon side of this thing, which I'll get to a little more later, which is basically saying, well, concrete, obviously intensive. We need these foundations, but the piles are steel. And the steel, we can try to find recycle steel pipe to build a lot of those. The steel structure itself, steel is also fairly intensive, but we can find local fabricators to reduce that footprint, which we did. And then the wood is very helpful. There's a lot of wood in Oregon. But what if there was a way to figure out to really maximize the benefits of wood by being very specific about where it comes from? Because if we can bring the wood in from forests that are managed very responsibly, we actually get more benefit. And so that's a little bit what I'll get into here. But first, again, construction management folks, shout out, come on. I want to share a little about how we built this thing, because to have a conversation about how you build it and what you build, for this project, that's the same conversation. You can't build this thing, you can't even imagine this thing without first and simultaneously thinking about how you build it. Our mandate was to keep the building going. The planes had to keep going, right? The passengers, up to 20 million a year, had to make it to their flights, which means we had to build this thing in such a way that couldn't get shut down, ever, right? There is no day off for an airport, right? And that meant we couldn't use big cranes to lift things into place, because that would mean you'd have to shut down these spaces down here, which have to stay open, right? So the city of Portland required that if we were gonna do this, if we're gonna build in place, we had to come up with a way to slide things over so that this stuff below can stay operational, right? And that changes how you think about it. It means that, if you're sliding it into place, that means you're building it somewhere else and moving it over to the construction site and sliding in place. And so one of the illustrations we did early on was this. It was like, okay, so what we need to think about is building a new column idea, where all the tops of these columns are at the same height, and this roof thing slides almost like rail cars into place, right? Which is what this illustrates, is the idea of kind of sliding things into place. And this is a section, okay? A little bit of architecture section here in a real clumsy way, but hopefully it makes a little sense. So here's where you get dropped off at the airport, cutting through it, looking through an airport, right? You get a ticket hall. That's your front door, existing front door. Below that's your bag claim where you get your bags. All these colorful things, these cannot be turned off. These have to stay in business. They have to stay in operation. So when you think about building new over that, you have to minimize the amount of time that a new column comes through this existing stuff. Like this column over here might cost $1 million to install. This one probably $3 million. You know, because like if you're coming through an existing building, it's painful. You got to get stuff out of the way. You got to keep things operating, right? So you have what's called enabling projects going. So you got to come up with a way to, basically, I imagine what I always describe as building a table over another table and trying as hard as possible not to kind of interrupt that first table, right? You just kind of tabletop over. So the next set of columns is there, outboard, and then way outboard, right? So you have to keep things going as you slide the new over, and you can demo the non-essential, the retail spaces, offices, the non-essential stuff gets demoed, and then this existing floor gets upgraded in construction. So here's the diagram what that is. It's like you get these columns at the same elevation, and then the new roof shares that same level so that you can slide it into place over those columns, and that these things then are what we call modules, roof modules. And these are big. This dimension in this model, these are 150 feet apart, so the total length here is close to like 360, say, big cantilevers on the end. This is actually a 65-foot cantilever. So these are big, super modules, and then these modules then can be very specific to the spaces below them. So that's what we do, is come up with a very regular frame, but then within the frame, very specific kind of roof shapes and interventions that could help frame the spaces below. And here's like how those things come together. So like all the dark colors here are what we call phase one, and then the phase two stuff are the leave outs, because you have to keep security going, right? You can't shut down security. So the existing security lanes are here, and what'll happen is later this summer, the security that's here and here now will turn off, and the new security we've built here and here will turn on, and the passengers will be redirected. So instead of having to go this like this, they'll go straight through the new to like this, and then this becomes a construction site for the next 2 years. Very simple phasing, right, which the contractor loved. When we initially had like 23, 24 phases to the project, and we reduced it basically to 2, like because of just this idea of the module, which is repeated. This is a repeated version of that. This is a repeated version of that. And these things all get built off-site and then stitched together in a very specific way, which this diagram kind of shows as a model of the modules coming together. We slide them into place over the existing building, and from the airfield on this side, slide it. And then these 2 darker volumes here, those are the kind of workhorses of the airport. Those are like your air handling units, your mechanical stuff, right? And then this illustrates that kind of quick process here. So you get the columns getting dropped in, the roofs coming into place, right? First over the existing, and then off the 2 ends off the concourses, and this kind of mega machine moving them into place, which I'll share with you. So pretty unique. These are like 1.3 million pound mega modules that are built off-site and then slid into place to make this new building. And that off-site happened to be right down the airfield from the existing building. There's the main terminal there. This is where they got built, called Fab Yard, 1.2 million square foot Fab Yard, just to the west of the main tarmac and alleyway for the airport. And this got built right away. So the first thing we did is build this. And the reason we did that is schedule compression. Because normally, you demo something, you get ready to build the new thing, you start building the new thing, you work your way from the bottom up. Here we went top down. No, let's start with a roof. Let's get that going right now, because we can get it, we know what it is. Let's get it going right now. And that allowed the demo to happen at the same time, and that allowed people to move out of their offices and get ready for the new stuff at the same time. So it allowed normally the things that get stacked up to the beginning of the project to all happen at the same time. right? Which reduced the amount of construction time tremendously and also helped with that whole budget pie chart thing. And this is what a fab yard looks like. So the cool thing here is that, you know, when this is in place, this thing will be 60 to 75 feet in the air, and you imagine how hard that would be to work on. Well, in a fab yard, if it's prefab, it's 12 feet in the air, right, which is a pretty typical ceiling height. So you can get armies of people on these scissor lifts, you know, doing their work in a safe way, right, and they can talk to each other. They're all local to each other, and they're up against a construction fence, so they don't have to go through TSA to get to work. They save 30 minutes every day. That has a dividend, right, on the dollar side. That helps make this really pencil out from a budget perspective and make a lot of sense. Like, well, actually, this could work. Is kind of where we landed with the estimating team and the contracting team. Let's do this. And so here's an image of the fab yard a couple years ago, and here's from the inside looking up at that new roof, right, getting built. And it was built in its entirety. So the roofing's on this thing, the structure's there, the acoustic kind of baffles are in it, the fire protection system's in it, the lighting is in it. So that when it's pulled out of that fab yard, we call it like unzipping. You know, when you unzip this thing, you have to build it all together, and then you have to design zippers, you know, to make sure you can pull it apart, because it's got to move its way over to the airport. You know, it all goes together, and you don't want to go back up on that roof and reinstall something. And you have to just get as much done as you can here, so that when you move it over to the airport, it's as done as possible. And here's kind of an image of just a study that we did with a company in Canada designing the assembly process. So again, back to that construction thing, you know, working on how do you design a zipper so you can unbolt the steel parts of the roof and slide things out and rebolt them together, you know. So that's what this is, and this is you see some of those columns here. You see this is just one of the modules of the roof sliding out of place. But we did this to illustrate sequence, you know, to illustrate to our contracting partners and the owner, the Port of Portland, how this could happen in a safe way, you know, and how we can manage the risks associated with moving big things around. And this is one of these modules, right? So it's a kit of parts of primarily girders, which are the kind of straight lines on the edges here. These are steel. They're basically bridges, built the same way as it's a bridge girder, steel bridge girder. Very simple and also almost a commodity in terms of price. Simple. And then it's wood. All the stuff going in this direction is wood. Big wood beams that are all made in Oregon and have different geometries. We only have like 7 different arches, but we create loads of different shapes with just those 7 arches. And then skylights, which are subtractions. You know, so over the columns, there's a kind of a round structural beam that actually became a skylight. Over the landscape elements, you get these big skylights. Over important moments in the plan, you get these smaller domes, almost like the Parthenon, say. And those all mark space. And so when this thing got moved, this is the lead superintendent, Jason Koski, who basically the buck stops with him here. And he was like the first night, the first one moved into place, he was standing there like, you know, it wasn't a cross your fingers moment, but boy, he was sweating because this had to work. There is no option for failure here. This has to work. If this thing collapsed, the entire state would shut down, right? You imagine how many jobs would be shut down because the airport doesn't work for several years, right? This is a no-fail option. And so this is the first one going into place. There's all kinds of contingencies and kind of safety thinking about how to make this fail safe, but he was responsible, and this is him standing watching the first module go into place, and here's a few more as they work their way into place. And this is a short video showing what that looks like. So crews working on the module, getting the lattice installed out in the fab yard. There's the fab yard, and the roof is in its complete form. Here it's getting unzipped. And a company from the Netherlands kind of came over, and Houston came up and brought their equipment from Houston ultimately, but it's Mammoet. And they were the team that figured out how to move it, right? And so they come up with these big steel elements that are basically you know, jacks and robotic feet that move this thing to land on those columns, right? And so here you see it moving across the airfield at night. We got a 3-hour window between the last flight and the first flight. So like think 12:30 a.m. to 3:30 a.m. kind of time frame to move this thing over. And then when it lands, it lands on a column, and it'll get slid into place with what are called strand jacks that pull the roof across the columns, and allow it to kind of very delicately work the way there's, as you might expect, a lot of grease involved here, lithium grease, to get it in place. But it allowed us to keep all of those baggage handling systems, all of the people that are getting passengers to and from their flights underneath this construction, keep them working, right? So that work can keep going while the roof is being slid into place over them. And again, these are very big elements. These are I think the biggest one's like about 200 feet by 100 feet, and 1.3 million pounds is the biggest one. But and then they get kind of stitched together, where there's the primary girder, and then there's infill elements that slide between the two steel elements. So a really challenging construction problem that a very big team of very smart people, engineering, contractors, the owner, architects, everybody's working on this. Like, how do you think through how to build something over an operating building that completely turns upside down how we think about our sequence through here, right? So that roof, though, was thought of as a systems umbrella. And so we started with the idea that, like, to the point, again, a park, right? And Portland has a lot of great parks, especially Forest Park on the left, where I take my dog for a walk. The idea of walking under a canopy of trees, how can we design this roof to have that feeling of walking under a canopy of trees? And we explored, like you guys do here, a lot of models initially were spanning between columns, again, long span structure, in a roof that allowed light in. That was a key thing for us. How do we set up a roof that allows light to get in? And these are some early ideas of structural systems that allowed us to introduce daylight in different ways, but to use wood, and what, kind of wood in a normative, I will say, so beams, plywood, dimensional lumber, nothing exotic or impossible to find. These are commodities in Oregon, but you're assembling them in creative ways. And this is kind of early sketches the team did on what is that, columns which split the load of the beam in half right away, and give you this kind of zone where that steel is to run all of your rainwater, your sprinkler mains, all of the mechanics of the roof can wind up there. And then you shape in between these vaults, and those vaults can have specific shapes tailored to the spaces beneath them. So under the ticket hall, they're domes. At the perimeter, they're vaults letting light in. And then other lights, skylights between them. So here's that kind of geometry. Columns, right, 100 feet apart, big glulam beams with lattice underneath, steel girders between the columns, but this is a 100-foot span, and underneath that, and it's 38 feet in the air, you get other structures which are concession structures, trees, light posts, and so this starts to feel a lot like a street, and in fact it is a street, and in fact it's exactly dimensioned off of a very important Portland street, the 23rd, which is our main retail street. The dimension between here and here matches exactly the dimensions on 23rd Avenue, which is our like feature retail street. So you get, your coffee shop, your kind of like sidewalk dimension here, and then your thoroughfare dimension there. So it's set up to be familiar to the streets of Portland in a very specific way. And the team kind of was exploring, well, what does it mean to get at that roof and get light in? And here, models. I saw models upstairs, great. We lived in models for years on this project. And we had teams building fabulous models of this roof to explore specifically how light and how construction, not just how light, but how construction also could be thought through. And so here's Talisa of our model shop, kind of going to the fab yard with the first model she had made of one of these modules, kind of proof of concept, and it's a really proud moment of like, well, I contributed this thing to the thinking of how this could come together, even at that scale. And then also building models of modules to explore how light would get through the roof, right? And this is a heliodon study showing very specifically for one of the vaults how light would get through. And it's not just any light, it's all kinds of light, right? So it has to have a variety of experience. It's important that some of it's direct for landscaping elements, some of it's dappled light, for different parts of the program, seating areas. dappled light, for restaurant space, maybe dramatic light, to punctuate different parts of the plane, so direct sunlight on the floor. But mixing it up, sometimes it's controlled, sometimes it's not. And doing that in a very distributed and careful way. So skylights are expensive to maintain. You don't want to have too many, but they do a lot of work for you. So the thing here was, how much can we just rely on daylight for this whole airport? And we wound up with it. Basically, over 60% of the floor plate was above 300 lux, which is fine to work, to walk around in. So most of it is daylit. And some of it, that daylight is punctuated, the dark red. And in fact, now the construction team, when you go there, they're just relying, they don't have lights. The roof's on, but they're just using the skylights to build the building. And that the roof also could have geometry to it. We call them light baskets to catch more light and to bring it down into the space. And so here are some of the more, I would say, prominent ones in the middle of the building, where the roof peels down and it kind of allows light to, like, imagine a lampshade, right? Kind of glowing under here. And here's an image of like the different kinds of skylights, so a vaulted light, direct kind of punctuation light over a column, and then some of these big lampshade light baskets, we call them, over landscape elements. And this is just a real quick kind of summary image. I'll kind of skip over this because we've seen some of this, but of all of those different skylight elements on the vaults, you get a sense of where they are. And all the skylight elements were built out of mass plywood, like these little hexagon shaped things, right? And then we put a fairly conventional skylight system over that. And these models are done not for the client, they're actually done to help the contracting team, the people building the building, understand how to build it. And they can have conversations about sequence and getting people in and out of spaces. These are those light baskets from below. Now, just last week, part of my team here visiting. But you see these are 60 foot by like 20 foot skylight elements that bring light into the space. And then the curtain wall. So the curtain wall, and I'm sorry for time here, I'll try to speed up. The curtain wall is part of this resilient system. A curtain wall hangs. Right? Think of a curtain, curtains hang. The curtain wall hangs from the roof, not unlike a tablecloth, right? So this was the concept for the curtain wall of the building. The curtain wall of the building is, yes, it's a big box, 1,000 by 400, but also includes many kind of very specific edges. The key thing to appreciate here is that big curtain wall has to move with a roof that's moving 44 inches, as Pam said, right? So 22 inches in every direction. That's a lot of movement. Nobody's ever done something like that in North America. And the curtain wall has to do things very specific for the occupants behind it. Some people like to be, they like colder environments. Some people like warmer environments, right? But there is a diversity of experience that's important to support all along the perimeter. And that diversity of experience was a layer, right, that we add to the curtain wall of kind of sun shading and glare control that hangs with the curtain wall. We did a tremendous amount of analysis, if we're going to control glare and sunlight, where do we do it, and how much of it do we do it? And we did that analysis to study both visual comfort, so how much sun is hitting the floor at very specific areas around the perimeter, and also first cost, like how much can we reduce the cost of the cooling for this project because we're adding cost to the curtain wall. And we did it for every elevation. We did it for the horizontal elements, below the vertical elements. And in some areas you get fairly significant first cost reductions, 18% to the cooling load for this whole elevation, which has real dollar kind of consequence. Some are less significant, but you bounce them all, right? To wind up with something that was this, kind of a Swiss Army knife. We call it high performance, low profile. So it's at the passenger level, down here, low, it almost goes away. There's no mullions, it's just butt glass, it's jumbo glass, 10 foot by 14 foot tall, jumbo glass with no mullions. The goal there was just to kind of deliver some magic, right? So like you're a young kid, you go to the airport, you want to see airplanes. Airplanes are big things, right? Hundreds of feet wide, and they're right in front of your face, right? So you want to see wingtip to wingtip. So you wanted to have that experience of just seeing the entire airplane as you approach the perimeter of the building. As you move up and you see the clouds, right, and you need to control sun, the density of stuff increases, and so we get this kind of grill work up above. This is a section on the right of a curtain wall here. This is kind of a diagram of it at a chunk of the building. And here's what it looks like from inside. So from inside, it should just be gone. You shouldn't be here. There should be nothing there, right? You should just see airplanes. You should see the hills of Portland beyond. It's not about the glass, right? You want it to just be gone. But as you move up, it has work to do, right? It has to control some of that sun. So the stuff starts to show up. And from outside, again, this is just a view of how you kind of relate to the volumes. But it hangs. This is hanging from the roof down. And when it comes down, or first talk about how it's set up. This is a mullion. So you think of any mullion in a glass, right? You've got glass, you've got structure to support the glass. That's the mullion, the gray thing here. Glass, structure to support glass. Typically, you wind up with something like this when you're doing a big building, where there's structure, and it might be 2 feet deep inside the building supporting this glass, and then something outside for sun shading. This structure is 2 feet of your building. And when you're spending between $3,000 and $4,000 a square foot, that's lost revenue, right? That's not useful space. So we kind of, our first thing was like, well, can we flip this, get this outside the building so that the owner can lease this space out, right, and make revenue on what's on the inside. They lease to airlines, they lease to concession spaces. And then can we start peeling this down so that thermally this has very little points of contact to glass to improve how this thing is performing from an energy perspective, and that this outside part of it is helping shade that glass, right? And then we refined it and wound up here, where this is kind of the mullion of the curtain wall, where it's basically the glass is pin supported by the exterior, which here's the detail on the right, a little bit of architectural detail. But you see it's very minimal, right? There's not much there holding that glass. There's structure outboard. There's a little clip that the glass hangs onto, and then the sunshades on the inside, the glare control elements are supported. And we did a thermal analysis kind of proving that this actually was really giving us a lot. This is a very high-performing curtain wall from a thermal standpoint. And here's kind of like some detail, like that stuff kind of aggregates to something like this. We get 10-foot spacing, and we call this is jumbo glass, right? They don't really sell this at your local hardware store, right? This is very special glass, and it's very, very optically clear glass, that it's allowing very good color rendition through it. It's very flat. It has to be because it's also acoustic, right? It's laminated. There's airplanes out there, right? So it's doing a lot for us, but the goal was, in spite of all of its technical kind of criteria, to make it just kind of go away, because the real show is the landscape. It's the river out there. It's the plains. This is kind of a washed out image, but it kind of shows you how minimal. From inside, looking through it, there's not much there, which is the point, right? Movement. That system then moves a lot. The roof is going 22 inches each direction, so that move, it's hanging up here and it's sliding down here. So it's got to slip. So as the earthquake's happening, it's slipping left, right. It's pivoting from the roof, rotating, and then when there's snow on that roof, it's also got to go up and down 4 to 6 inches. So there's a lot of movement and a very complicated, this is kind of like, you draw details in architecture. Some details are really, really, really important. This detail had a lot of people working on it for years. This is like a multi-million-dollar part of the project, to get this right. And the amount of things this needs to do to get this building to function was very critical. It's hard to understand maybe, but it's diagrammed a little bit here on the left. This is a moment in the project where that roof that's hanging down connects to the roof, which connects to structure, which is coming off the floor here. So it's got to slide in one direction. It's got to deal with the snow loads 4 to 6 inches vertically. And then it's got to also allow rotation when that big earthquake comes, because this glass cannot fall off. That'll hurt people, right? It's got to stay in place. So that's what it means. Then we had to design these doors. Oh, this is a nice little thing here. So that slip, pivot, deflection is illustrated by a video which isn't playing, so I'll keep going. Which we tested, right? We test these things. This is one where it's sliding, this is a rotating, and this is a deflecting video. Here it is getting built recently. Here it is from the outside. Again, jumbo glass, but it's headed towards completion. So lastly, I'm sorry I'm running late. Talk a little bit about sourcing, because that's a big part of what this building is. Farm to table architecture, right? So when we go to a farmer's market, we love it. We know who grew those carrots, right? That lettuce, right? We have an immediate understanding of the basket, you know, that it took to kind of deliver that food to my table, right? It's kind of, you have, the values are beyond just the thing itself. You actually have the relationship also, right, with the people that grow the food. And that is kind of what we were driving at here, is how do you get away from the problem of architecture from, you know, you don't just go into Google and type in, give me a window, you know, it's like, how do you set up the many hundreds and hundreds of relationships to get something like this built in a way that sustains them, right, in a way that creates a very real kind of identity for the project, which isn't just carpet. It's great carpet. It's endearingly garish, as they say, right? But that carpet, right now is what their image is, right? But how do you actually tie the building directly and contractually, like with contracts, to the industries of the region, right? And that's what we were challenged to by the Port of Portland, which was a fantastic client. It was like, for them, that was crucial. It's like, we've got a mega project here. This is a must do. So how do we make it from the region? How do we really use it as an opportunity to leverage community resilience? You know, how do we kind of set new standards for environmental stewardship, and how do we really illustrate the problems of embodied carbon with this project? And with a wood roof, this is the normal way to do it, right? When you buy wood in a lumber yard, you don't know where it comes from, right? The wood is cut in who knows where, and it winds up in something like this, which is called a log deck, and it's mixed, right? It has no history. It's anonymous, right? That's business as usual. That's on the left here. Business as usual is, in the best case, you kind of can say you're from the area, you're from the region, right? And you're sourcing your project from a region, or from, like LEED would say, from an arbitrary circumference, right? But forest to frame, which is what our project and others in the Northwest and now nationally are doing, is how do you set up contracts directly with landowners, growers, fabricators, mills to supply projects, so that when it's delivered, you can point to that beam and say, hey, that's from this family farm down the road, you know? And so you get the benefits in terms of the equity, you get benefits in terms of carbon, because you can be very specific about the carbon story for each stick, but especially you get that kind of like the benefit, which is a little less tangible, which is like the relationship, right? The investment, the community presence in the building, which is a very real presence. So here's that business as usual, you know, forests, log decks, mills, and lumber, right? This is a sorting machine, you know, diagram, which basically at the end of this, you have no idea what you bought and where it's from. Transparency, so creating transparency, just asking the question, well, where does this come from? You know, how do I know where these logs come from? So is it from forest A, B, C, or D? I don't know, but asking the question, demanding an answer, starts you down a path which leads you to something like this, segregation. Well, okay, if it's important to you to know where it's from, I need to set up the mill owner needs to set up the contracts differently with the forest owners over here, so they can start to identify and segregate the wood in very specific ways, right? So that at the end of this thing, you can point to your building and say, oh, this family supplied this wood, right? Or this tribe, in our case, this tribe supplied this wood. And so that at the end of the day, your whole building, in our case, it's like almost 1 million square feet of lumber, we can point to every stick and know its origin story. Whether it's a tribal land, whether it's a small family farm, whether it's a nature conservancy, whether it's estate lands, you know, whatever it is, but they all have a presence that's specific and actually will wind up getting, you know, a tag on a wall, you know, saying this is where the wood comes from. And here's some of those landowners on our project, you know, a tribal, Skokomish tribe, Hyla Woods, a small landowner in the Willamette Valley, the Nature Conservancy, right? Family woodlots, which are very common in Oregon. You know, it's not like a farmer here, right? That's a family farm, and each of these have different goals, right? Nature Conservancy might have a wildfire resilience goal. The tribal lands might be looking to do more forest restoration. For a small family, it's really about maintaining that wealth within the family, right? So how do they set up a new kind of contracting scheme? And then we're able to map out all of the ones that supply the airport. And it's not just the landowners that are supplying the wood, but it's also the fabricators, right? The next in line, the people cutting it and milling it, right? They get specificity. The lumber mills, they get specificity. So all along the line, you kind of know the entire chain of supply. And why does that matter? Well, why that matters especially is because then you can be specific about who's supplying your wood. On the left is business as usual, clear cut, right? This is, again, anonymous and also carbon intensive. On the right is a forest managed differently, right? Where a lot of that carbon stays in place. It's called biogenic carbon, right? So trees that stay in place. It's harder to log this. You know, you got to get your machinery in there and you take some trees, but don't take all the trees because wildlife needs this. This helps prevent wildfires. This is like wildfires just roll across space like this. But a wildfire here, there's not much to burn down low after they clear this out. It actually is much more resilient for wildfires. So there's a lot of good reason to do on the right, but for our project, it was carbon, part of the carbon story. So we learned that, you know, if you can account for the wood that stays in the forest, the biogenic carbon, and measure it in a real specific way against the amount of output, the carbon sequestration story changes dramatically. So yes, wood is more efficient than steel, say our alternate building products, between 6 and 15% better in terms of its carbon story. But as soon as you start also accounting for the forest practices of where that wood comes from, that savings jumps from 18 and 40% depending on the forest management. And in our case, we kind of landed at like a 30% improvement over baseline by kind of being specific about the kinds of forests the wood is coming from. And that matters not just for the wood lot owners, but also the fabricators, right? So that a glulam business, this glulam is a beam. This is glue, laminates of wood, right? This is Zippo Lumber in Eugene, Oregon, where I'm from. They shut down their glulam mill in the 80s. Like a lot of people, they shut down. But this project allowed them to restart. They invested in a new plant. They hired more people, and so that industry that's on the rural urban fringe, say that the kind of mills and the fabricators were able to kind of jumpstart because of this project, and kind of a new market was created for them that they were able to take advantage of. And so finally, I'll try to wrap up with craft. So not unlike the wood story, other industries benefited from this project, including the steel industry. The columns here are really unique. And they're made right across the river from the airport here. It's kind of a 9-mile loop over here. I guess here they might call that a Michigan, I don't know what I heard this term, Michigan loop, this kind of U-turn, right? So this is the U-turn from the airport across to the steel mill, and it's the same steel mill that built those Liberty ships, right? So the Liberty ships were built right here. That's where the airport is. There isn't an airport in 1945 here. It was somewhere else. But there's the airport now. So right across the river from where the columns are made in the old Liberty ship mill is where the roof is made. So there was this kind of fantastic charge to the steel fabrication yard because of our project, where they were able to scale back up their whole operation to basically into a new level engagement in the fabrication side of steel. And here's some of those Liberty ships getting built, and here's the columns being made at Thompson Metal Fab across the river. Beautiful work, right? Beautiful work. Craft here. You have to appreciate the craft. These are not covered up with fireproofing, drywall. This is just beautifully made things. There's no fireproofing on them, and that is a whole nother lecture of the largest appeal ever written in the state of Oregon. Finally, there's these elements under the roof, concession spaces, so bookstores, coffee shops. These are also timber, and these were designed in a way that allowed us to set up the contracts that a lot of people could get engaged in them. So yes, they're mass timber elements. The biggest ones are like 60 by 40, single story kind of little pavilions in an airport. But they're set up of a kit of parts that could be bid out separately to smaller shops. So a roof lattice, beams, and other kind of glass elements that the different smaller shops were able to kind of get the contracts for those. So here are those under construction recently. Here's one of those shops, Superfab. Formal model makers in an architecture firm started their own fabrication business. And this project allowed them to kind of grow dramatically. So they went from making architectural models to making massive amounts of stuff for the airport, because it's the same tools. Like the tools you have in the basement here, these like CNC machines, that's what built this stuff. Like it's the same tools. Like they learned that in architecture school, right? And they were able to kind of set up a shop and be awarded very significant contracts because of what they learned in a place like this, right? And here's like one of those concession pods, and this is what they got engaged with. They made the lattice, which is the stuff that hangs, that creates the kind of ceiling plane of these concessions. This stuff, they came up with a way to prefabricate it, and they called it flat packing, like you do in IKEA. You buy a wardrobe or whatever, and it comes all folded, all these miserable little connections and stuff. But they came up with their own version of that to flat pack this stuff, bring it in on dollies, and kind of slide it into place. You know, here they are making these flat packs of these panels, prefabbing them in their shops. And then they contracted then in turn with a small Native American company that does beautiful steel work, also digitally, cutting the steel elements that connect the dots on those concessions. So here you see the steel elements, just wonderfully made stuff that is part of these concession elements. And then here they also did these elements. These are like these barrels, which the TSA will use to interview people that do something wrong. You know, so this is where you go if you've been bad in the security line. We're going to give you these beautiful little Douglas fir saunas, you know, that you go into and have questions asked of you. But they came up with a way to again, flat pack them. You see they have these little QR codes taped to the ends of them, and they're all built in parts, and they're on these dollies, and they're brought in. But it's the thinking they learned in the architectural model shop that got them to this. And then finally, they made these, this is called a seam, which is a wall of lattice that helps create separation between the pilots, say, that are going, you know, through the security lanes and the public. It also helps to separate retail spaces from people queuing in the security lanes, and it's huge. It's 500 feet long. And it was designed in collaboration with one of these shops. Like, how do we design this so that you can make it? How do you design it so that a small shop like you can be awarded a contract to build this thing? And it was kind of set up, again, like a kit, but set up with a kit that starts, you know, on a CNC machine table like you have downstairs, and it's just pieced together. And it all sticks together, and then here it is in their shop just a couple weeks ago, as they're working on it right now, getting milled into place, right? And then they're putting it together as chunks that'll be brought out to the airport. And then finally, sorry, this is the final one, this story. So this is a small family, Ben and Sarah, this is Ben, this is Sarah, in the mid-Willamette Valley that are woodlot owners. They own about 1,500 acres of primarily oak. That's oak. Oak in Oregon isn't harvested for lumber. It's pretty tough wood to use because it grows like that, right? It's not straight. Typically, that's what happens. When they do a logging operation in Oregon, you get a slash pile. That's a slash pile. And typically, that slash pile is burned, right? And so Ben and his mom had the idea, well, hey, is there a way we can start a business that actually responsibly harvests this oak and does something with it? And so they got into the flooring business. And oak makes good flooring, but you have to get really small pieces, you know? And so Ben, who's a super creative guy and really into machines, got into the idea of parquet. And he went to Germany and learned about parquet because there isn't a parquet plant in the United States. Well, there is now, but there hadn't been one for years, many decades. But he went to the local ag school, Oregon State, and he bought out of their old wood shop, he bought their old plane to plane the wood to flat. So the logs start here, and then the plane that he rehabilitated from the ag school is right there. And then it's dried, right? And then it goes through this thing, which Ben assembled. He had to go to Germany and learn how to make this thing. He made this little machine which makes parquet flooring, if you remember what that looks like. You don't see it much anymore, but it used to be a thing, right? But they make oak parquet flooring, and to do it, you got to get that oak really small, right? But then it becomes, once it's made really small, little pieces, then you don't have the problem of the twisting and the crooked wood and stuff. It actually becomes useful again. And so his idea was, hey, how do we make something out of these slash piles, and how do we create a new market? And that's exactly what he's done. This is a parquet machine that he's assembled. So he rented a small warehouse below his forest near the city of Salem. He employs about 10 people, and they make parquet flooring. This is a pallet oven coming out of that machine, and oh, good, it works. So here's the machine, which is fascinating. It's basically a sewing machine. Parquet flooring, I didn't know this, is a series of little sticks all put in a line. The back gets routed out, and they sew it together with wire and then cut it, after each piece is made. So that's the wire spool there, right? Coming in, wrapping underneath each tile of parquet, and then it's kind of clamped into place, and then it gets spit out at the end here as this beautiful little tile, right? That this person's checking to make sure they're straight, right? And because they all got to be square and straight, and then palletized, and then, in our case, sent to an airport. And that becomes our flooring, right? So here's parquet flooring getting glued into place, which looks like this. It's gorgeous, right? But it's also very appropriate to an airport. It's flat, it's massively durable, right? And its wear layer is the full thickness. So you can sand this stuff till you're down to concrete, right? And it's still useful. So this thing has like a 50 to 60 year lifespan. So it's way better than carpet. And it's as good as terrazzo. And he's got a huge amount of it yet to do. He's got a lot of work to do, but it's beautiful, right? And it's kind of that small family. We'll be able to point to that. We know exactly what forest it came from, right? We know exactly how far they drove to deliver it. And every bit of the building, we'll be able to kind of say this flooring, came from Ben and Sarah down in Salem. And so this is what I want to leave is like, and that to me is the new potential of this project, is like this on the right, I don't know, this might date a lot of you, is a suites catalog, right? So before Google, us architects relied on this thing on the right. This is a catalog of products set up by divisions, right? So if you were looking for that oak flooring, you might look in Division 9 here for oak flooring and then order it. And like a catalog. This is back in, I would say the 80s, right? Maybe this ended. But it's anonymous, right? You're just picking stuff out of a catalog. And a lot of construction happens that way. Now with Google or whatever, you don't have this on the left. And this on the left, we think is the real opportunity here, is that it's not just that the thing is, its footprint can be measured very specifically, but it's that especially you're lifting that family up. They're employing people, right, from their community, and it's that rural-urban line that's so critical to all of us now that you're helping to elevate, right? So that's kind of the punchline here, is that is the opportunity that we see with this project. And it's not just airports, right? It's everything, right? Can be kind of structured differently. And just some parting shots. So yeah, start with a model. You go to the rendering, that's the central part, and then you kind of wind up with just like last Friday, looking at it. We're almost there. Sorry for running late, but 8 years condensed into about 70 minutes. Yeah. Questions? Yeah.
I talk about the type of glass you use. I assume it's fairly, there's slight adjustments for each size of the building, but how did you balance getting that very clear colored glass?
Yeah.
With the difference between glare and transparent? I know you explained a little bit about your structural systems, but what about the glass itself?
Yeah, the glass itself is really unique. It's jumbo glass, right? And it's laminated glass within a space and then another piece of glass, and it's almost 2 inches wide total, right? So the glass itself has, and if you know glass, solar heat gain coefficient of 0.21, which is very good, right? Because of the coatings on that glass. And its VLT is, I would say, compromised because of that, right? So it's a VLT of like 39. So it's still pretty good, right? It's still pretty good. But we did a tremendous amount of exploration with different kinds of glass, and we had to bring the CEO of the airport, you know, to agree that yes, I'm willing to spend this many millions of dollars on this glass order, because I agree it is both performing and transparent, which is always a balance, right? Because you want to see that river, you have these promises about you can see the clouds and you can see the shapes of the clouds and the geometry of the clouds, and that's important to the passenger and the experience of being in this building, but it has to perform, right? And this building, the new part of the construction is like more than 90% glass, which is crazy. We can do that because we have a very big roof. So most of our envelope is horizontal, right? And the thing that section of the perimeter, which is between 38 and 58 feet high, is almost all glass. Yeah. Any other questions from the construction management? No. Yeah.
Assuming that the original roof was not a prefab system,
Yeah.
what was the process or how difficult was it to remove it while remaining fully operational?
Okay, that's a good question. So how do you demolish a building and remain fully operational? Carefully and surgically. Most of the hard demo, which is the steel demo, is done, again, late at night, right? So you've cleared out an area, right, to the best of your ability, and you cut it, and you remove it in very small pieces. It's slow. And because it's so slow, because you can't just take whole chunks off, there's no bulldozers here, right? You're having to cut it into little pieces and to make it safe, right? They have to be little chunks that can basically fit in a small bucket to get out of the building. That takes time. But we had the time because we built the other roof off-site, right? We bought time to be safe, yeah. Yeah, yeah.
So you mentioned the portion of that building has you made it so it's accommodating for earthquakes, or you've got the ability to move.
Yeah.
Is there any other parts of that building or that structure where you have earthquake bracing, or is that just that section there?
Yeah, so the earthquake story here is all of those new columns are the bracing, right? So they're cantilevered structure. In other words, they're self-supporting even in the earthquake. They're very rigid, right? So there's 34 new columns which replaced almost 700 existing ones, and long span between them. That means all of the roof is earthquake resistant, and everything attached to that roof is. That doesn't mean all of the floor is. Some of the floor, which is existing building, will collapse. But everything that's new will stay. And so we worked with the client, and it was important that the new stuff had to be critical, right? So it's all the electrical systems, it's security, it's TSA, so that if the big one comes, most of the city's shut down, most of the existing airports shut down, they can still move people through there, even if they have to bus them to this thing, right? Good question, though. Yeah. Yeah. We don't have tornadoes, though. Yeah. Yeah, well, thank you all. I really appreciate the opportunity to come here. Yeah. Hi.
So would you say that since this was an organ and it is heavy on lumber production,